All right, today's lecture is going to be a review of periodicity. And periodicity is looking at elements that are in the same family tend to share the same properties. And that's because they tend to share the same number of valence electrons. But not only that, but also looking at what happens to some properties of elements as we go across the periodic table and when we go down the periodic table. And this can always be explained with Coulombic attraction. And that's something we talked about last year quite a bit in depth. Coulombic attraction is the attraction of the nucleus to the valence electrons. And the stronger the attraction, that leads to all these properties. And you should be able to predict these properties based on looking at those two facts. Now, whenever we go with a periodic table, we can either go across or down. So when we go across the period, when I go from something like sodium all the way across to argon, what happens to Coulombic attraction? Well, the Coulombic attraction, when we go across the period, increases across the period. Argon has got a greater Coulombic attraction than sodium. The question becomes why? What's the primary factor? The primary factor is when we go across the periodic table, the valence electrons are in the same energy level. And because they are in the same energy level, okay, and we want to use the word energy level. We don't want to use the word ring. But since they're in the same energy level, the distance between the valence electrons and the nucleus is not changing. All right? So what does cause this change? And the reason why is due to the number of protons in the nucleus. Increases. Okay? So, what happens when we go down a family? When we go down a family, so for example, like sodium down to francium, okay, Coulombic attraction decreases. And this is because the valence electrons are in higher energy levels, i.e., the distance between the valence electrons and the nucleus is increasing. And that causes the Coulombic attraction to weaken. The farther two oppositely charged particles are apart from each other, the weaker there is attraction between them. Okay? Okay, so knowing this, we now should be able to go through the basic trends that you're expected to know. Atomic radius is looking at the size of the atom from the nucleus out to the outer edge of the electron cloud, a typical radius of a circle. So, when we go across the periodic table, the atomic radius, I'm going to label AR, decreases. Atoms get smaller when we go across a period. And that's because if you're asked to explain or justify, you're going to say the Coulombic attraction increases because the nuclear charge has increased while the valence electrons are in the same energy level. That's exactly the wording you want to use. The Coulombic attraction increases because the nuclear charge has increased, but the valence electrons are found in the same energy level. When we go down a family, the atomic radius increases, gets larger and larger, because the Coulombic attraction decreases because the valence electrons are in a higher energy level. They are farther from the nucleus, which weakens the Coulombic attraction and also makes the atom larger. Okay? Ionization energy is the amount of energy it takes to remove the outermost electron. So if I'm looking at an element like sodium, 1s2, 2s2, 2p6, 3s1. The first ionization energy is the amount of energy it takes to remove the outermost electron, which in this case is the electron that's in the 3s orbital. How much energy does it take to remove that electron? That is the first ionization energy. The second ionization energy would be the energy it takes to remove the second electron, and so on and so forth. Okay, the second electron would come from the 2p orbital. The third ionization would come from the 2p orbital. The fourth would come from the 2p orbital. So when we have to make sure that when we pull these electrons off, we pull them off one at a time And we might be pulling from the same orbital for quite some time until that orbital is vacant and we move on to the next one. Okay? Now, typically with trends, we look at just the first ionization energy. Okay? The amount of energy it takes to remove the very first electron. When I go across the periodic table, ionization energy values typically increase. Why? Coulombic attraction increases. If there's a greater attraction of the valence electrons to the nucleus, it takes more energy to remove that electron. When we go down a family, ionization energies tend to decrease because the Coulombic attraction is weaker. It's easier to remove an electron that's farther from the nucleus because it's not as tightly bound to the nucleus. Okay? So you're going to start to notice that in all these trends match each other except atomic radius. Atomic radius is the oddball. If you know the trend for atomic radius, all of the others, Coulombic attraction, ionization energy, and electronegativity, all are opposite it. Atomic radius is the one that is different compared to all the other trends in periodicity. Electronegativity is the ability of an atom to attract an electron in a chemical bond. Again, when we go across the periodic table, electronegativity values tend to increase because Coulombic attraction increases. If there's a greater Coulombic attraction from the nucleus, it will attract electrons in bonds better. When we go down a family, they decrease because the Coulombic attraction decreases. If there's a weaker Coulombic attraction, it is harder to gain electrons in the bond because the valence electrons are so much further from the nucleus. Okay? One little side note with electronegativity. The noble gases have to be excluded from this trend. Noble gases have the greatest Coulombic attractions, but they have 0 to very low electronegativities, and that's because their outer shell is full. So while they have a great Coulombic attraction for the electrons, they do not want to attract other electrons in bonds because they typically don't bond because they have full outer shells. So this is one that does have an exception. So if we exclude noble gases, the element fluorine is the most electronegative, and it has a value assigned to it as 4.0. Fluorine is the most electronegative element because of the fact that it needs an electron to become full, and it also has the greatest Coulombic attraction if we exclude group 18. All right, a couple of side notes. Ionic radius. Ionic radius is the size of an ion. Well, if we have an anion, we have gained electrons. So if I'm looking at the sulfur atom compared to the sulfur -2 ion, the sulfide ion, who's bigger? Anions are always bigger than cations. Anions are always bigger than their atom state because when we gain electrons, there's extra electron repulsion, and that over the same Coulombic attraction, the nucleus still has the same pole, and that extra electron repulsion swells the atom and makes it bigger. Cations are the opposite. To form a cation, you have had lost electrons, and specifically, you usually have lost all of the valence electrons. And if you lose the valence electrons, then that means that you are down to the next shell, the next energy level. And therefore, they tend to get smaller. So the sodium cation is smaller than the sodium atom. So when you lose electrons, atoms get smaller. When you gain electrons, they get bigger. Okay? Last thing is something called an isoelectronic series. An isoelectronic series is a set of particles that all have the same number of electrons. So argon, the chloride ion, the calcium ion, and the titanium ion all are isoelectronic. If you count how many electrons each of these particles have, they all have 18 electrons. Real quickly, pause this lecture, and what I'd like you to do is think about it and arrange these in order of increasing atomic radius, or I should say particle radius, because not all these are atoms. Which particle is the smallest, all the way to which particle is the largest. Let's see if you can get this right and think about what would cause a difference in size, even though they have the same number of electrons. All right, the answer ends up being titanium is the smallest and chloride is the biggest because it comes down to the charge of the nucleus. They have the same number of electrons, so we have electrons in the same number of shells, energy levels, but titanium has got 22 protons, chloride only has 17. So the more protons you have in the nucleus, the greater the nuclear charge. Remember, the nucleus is really small, so even adding more protons doesn't make it very big. But because the pull of the nucleus has got a greater positive magnet, it will pull the electrons in more tightly, greater Coulombic attraction, which makes it smaller. So it always comes down to the number of protons. When you're answering these questions, think about two things. Where is the distance of the valence electrons? Is that changing? Or is the number of protons in the nucleus changing? And that will cause you to answer these questions in this concept. Okay? Again, thanks for listening. So you think of that nucleus in here. If I keep putting electrons in the same energy level, that distance between the nucleus and valence electrons is constant, or pretty much constant. There is a little bit of repulsion that causes this to grow some, but not much, not significant. So there's a very little to no change in the distance between the valence electrons and the nucleus. The nuclear charge, the charge on the nucleus, increases. It becomes more positive. Okay? So for example, sodium has got 11 protons in the nucleus. Argon has got 18. So because the nucleus has got 7 more positive protons, that pull on the electrons increases for argon compared to sodium because we're pulling on the same energy level. Sodium and argon, its valence electrons are on the 3rd energy level. So we're pulling on that ring with different amounts because argon has got more protons. Going down a family, sodium has got its valence electrons on the 3rd floor. The next element down, potassium, and so on and so forth. So as we go down a family, the distance between the valence electrons and the nucleus is increasing. There's a secondary fact, and that is we have more inner shell electrons. The inner shell electrons are the electrons that exist between the valence electrons and the nucleus. When we get more of these, there is a repulsion that develops between the valence electrons and the inner shell electrons, and that increased repulsion causes, again, a weakening of the Coulombic attraction. The inner shell electrons repulse the valence electrons, and that weakens the Coulombic attraction as well. But the big reason is the distance. That's the primary factor, but there's a second sub-factor that includes it as well.